Alright guys, today we're going to be looking at yet another problem under the backtracking pattern. Now this is going to be the second last problem that we are looking at. We'll just have one more problem after this, which will help us understand the importance of backtracking and how these exponential time complexities work and how we can kind of improve them by kind of using memorization and backtracking as a whole. So this problem particularly is going to help us understand pruning. Now pruning is a way to get rid of the branches in our binary or in our n-array tree to make sure we only go through the possible cases that will lead us to the final answer. We'll get into the example in a minute. So let's first see what the problem statement says. It says, given a string, return all possible palindromic splits possible. Now what are palindromic splits, right? So if we have a string AAB, we can split it at the first index, we can split it at the second index, we can split it after the third index. So if we split it at the first index, we are left with A and AB. Now is that a valid split? I would say that's not a valid split, because when you split it at index 1, you have A and AB left. Now if you consider these two substrings individually, you would say A is a palindrome because a single letter is a palindrome, and AB is not a palindrome because it does not read the same from both sides. It reads AB from left to right, it reads BA from right to left, so it's not a palindrome. All right. Now that we know these substrings that we get when we split at index 1 are not all palindromes, this is not a valid split. So we move on to checking splitting at first position and the second position, or so if we split at first position and second position, we'll get A, B, all three individual letters. Are they all palindrome? Yes, single letters are palindrome because they read the same from left to right and right to left. And now that we know that all of the resulting substrings are palindrome, this is a valid split. So in general, how many different splits can be done given a string of length n? I would say there are n splits, right? Or in this case, we have A, B, we have three letters, that is n equals 3. We can make 3 splits, right? We can either consider them individually, or we can split at the second position and leave out the rest. We can split at the first position and leave out the rest, and so on. So in this example, the output gives us 2 sets of splits. The first split is at index 2, which is 0, 1, and 2, and the second way of splitting it is at every index, so we get AAB. And the first one we get AA and B as a separate substring. Now B is a palindrome, AA is a palindrome again, so we are done here. So this is the output, and this is how the question wants us to present our output. So before we jump into the code, let's just try to draw out this state space tree for itself, right? Now the state space tree is going to help us understand what are the different states we want to go through. All right, let's start a new comment paragraph. All right, so let's just take this example. We have AAB as our initial string. So let's see what are the different ways of splitting it, right? The first way of splitting it is at after index 0, right? So if we split after index 0, we are left with AB. So A gets taken away. Now since we are splitting at the very first index, knowing that A is a palindrome. So let's take A away. Now if we take A away, we are left with A and B. What are the other ways of splitting it? We can take away AA because AA is a palindrome. All right, we can also take away let's just do this. We can also take away all right, center it like that. All right, we can also take away just B, right? So that's been covered right here. All right, so these are the different ways. So once we do like that, in the second level, we would say that we are left with, if we take away A, we are left with AB, right? So we are left with AB to consider. Now AB is not a palindrome, so this is not going to lead us to our answer. So this path of going from AAB to AB is invalid, so we're going to prune it. We're going to get rid of it. And the only way to get rid of such paths is by ensuring that you only go down that path if the remaining string is a palindrome, is a valid palindrome. In this case, A was a valid palindrome. You cannot go any further here because you're going to check if AB is a palindrome first. AB is not a palindrome, so you're not going to branch out and try to create B and A separately, right? Because that path is not going to yield you anything. So we're going to get rid of it. If you go to this path right here, if you take A away, you have B left. Now, since B is a palindrome, you can go ahead and you're gonna be left with nothing. Now, since you're gonna be left with nothing, that's a valid path, and so the split A and B is a valid path because it's gonna result in a null string at the end. You're gonna take away B at the very end because B is again a palindrome. So you do a palindrome check here at this level, you do a palindrome check at this level, and then you end up with an empty string. So you consider this path from going from AAB to B to null is valid, and so the splits are AA and B. All right, now that we understood our state space tree, let's just try to get our code in, right? So the first thing that I want to do here is just create a function, and I can call that function ways to partition. Now in that function, I want to pass in the string s. All right. Now I also want to create a function because we're going to do palindrome check, right? So I'm going to do is palindrome. Now is palindrome check is going to take in a word, and then it's going to check if it's a palindrome or not. And a very vanilla implementation of checking if it's a palindrome or not is by using 2 pointers. You start from left, so you say let left pointer equals 0, and then let right pointer equals word.length -1. And then you're going to run a while loop until the left pointer is less than the right pointer. And then you're going to check every time in each iteration if your word of left, the character at the left pointer is not equal to character at the right pointer, then you're going to return false. And then you're going to increment your left pointer to check the next character and decrement the right pointer. So you're converging into the middle. Very simple, very straightforward. Now, if it makes it through this loop, which is checking all the characters from the left and right, you're going to end up returning true, because there was no iteration which resulted in this condition, which is the characters are not true. All right, and now that our palindrome check function is ready, let's just use it. Now, before using it, this is ways to partition. Ways to partition is going to be a function called by the external caller. So we can kind of use our nifty DFS function as our nested function here that we can directly call. And there are advantages to using nested functions. One of the advantages is you don't have to rely on global variables. You can just create a variable here called result and let your nested function take care of populating this result without having to think about the scope of the result variable. So now that you have your function, DFS function, I wanted to take two things, right? I want to take the start index. I wanted to take the start index and the palindromic substring, right? So this palindromic substring is going to be all the substrings in our state. It's going to be AA, it's going to be B, it's going to be B, it's going to be AB and A. All right. Initially, the palindromic substring is going to be an empty list. I want this to be a list, and this list is going to contain characters, and I will only go with the characters that are palindromes. All right, the first thing that we want to check is say if start is already equal to the length of s given to us, which means we have already traversed everything from left to right in our given string s. In this case, again, just so you can follow along, AAB would be our given string. So if we are done going from the left to right, we can just store our result, and the result at this point is going to be stored here. So let's just use a spread operator to create a copy of the palindromic substring, and then we're gonna end the recursive call. We don't want any calls going forward. Now that we have created our base condition, the next step is to loop through all the ways of splitting it, right? I would say the first way of splitting it would be to start at start plus 1, right? So you cannot split at 0th index, you have to split at first index. And so if we start at, if we set start to 0 initially in our very first call, we need to start at the first index and see if we can split at first index, right? We can call this split to be more intuitive. And then once we have the split variable initialized to start plus 1, we want to run it through. Split is less than as to length plus 1 and split plus plus. All right, now inside each iteration, this is what I want to do, right? I want to first get the prefix that will be represented by our split. So we can say s dot slice, we can start at start at the start index, and we can say get me everything from split. So in this case, if the start index is 0 and the split is 1, we're going to get back a, given our string is AAB, right? So now that we have our prefix, we need to check if this is a palindrome. If it's a palindrome, only then we move forward and then create the other nodes. If we go back to our state space tree, we will understand that we are at this stage, AAB, and we are trying to check if A is a palindrome. If it's a palindrome, then we can move towards AB. So how do we do that, right? Check if it's a palindrome. We have already created our nifty function. We just need to call it. We say is palindrome, and then we pass in prefix. Now, well, if it's a palindrome, then it's very easy for us to do it. We just add this prefix to our palindromic substring. Remember, palindromic substring is going to be a list. And then we call our DFS function. We say, okay, A is a valid split. So let's move forward. So we say, okay, start. We can, the start is now updated to split. And then we pass along the palindromic substring going down the recursive path. And then once the whole path is traversed, we are going to remove the prefix from the palindromic substring. This is our simple backtracking template that we have seen so far in previous questions. And now that we have done this, we just need to see if we have missed anything. And I don't think we have missed anything. We just need to call this DFS function. So let's just call it. We would say DFS and start at 0th index and pass in an empty list so it can work with it. And then now the DFS function is responsible for filling or populating this result list. And then we're just going to return the result list once DFS is done with it. All right, let's see if we have missed out anything. All right, so ways to partition gets called. Let's just try to call it console.log ways to partition, and then let's pass in AAB, and we are expecting a 2D list with this kind of an output right here. Right. And let's see if we have missed anything. AAB gets passed in. All right, at this point we have initialized our result list, and then we have also initialized our DFS function. Start is at 0 initially, and then you have palindromic substring as an empty list. And then you're saying start is equal to length, start length. It's not. So it's not going to go in the very first recursive call. It's going to start at 1, and then it's going to go to the very end, and then it's going to say split plus plus. Now the first time the prefix that we get is from 0 to 1, which is s of 0 to 1, which is nothing but a, given our string is AAB. Now is a palindrome? Yes, it is a palindrome. So it's going to go into this if block, and it's going to call, it's going to push this A into the list. We're going to push it in, and then we're going to say call this method again. And now our split is, now our start is going to be updated to split, which is nothing but 1. So we're going to start at 2 in the next iteration, right? Start plus 1, and then we're going to pass in A. And I think everything is fine. So once we are done with all that, it's going to call it. Now we're going to end up with AB, Now we're going to end up with AB in here, right? Because we start at 1, we're going to end up with A, and then we're going to push in AA again, and then start will be at 2. We're going to start at 3 and so on. Once everything's done, it's going to pop it, and then finally we're going to get our results. So now let's try to run it on our online program is JavaScript compiler. Paste it in. Let's see what error we get. All right, we did not get an error, so I think everything looks good. We got our result as expected. These are the valid splits. And let's just look at the time and space complexity here. Looking at this DFS function, we know how many times it's going to do. It's going to call itself, right? It's going to call itself until we reach the end of the string. And looking at this function, this is going to take O of n time, right? This is going to take O of n time, because in worst case, if there are repeated characters in our word, then we're going to take O of n time to traverse the whole thing, given n is the length of the word. Now this is O of n. Now let's look at the DFS functions. Time complexity. It's going to be somewhere between 3 to the power n to 2 to the power n. Right? 2 to the power n, because every time we have a decision to make, then that decision is to split at a particular index or not. If we go back to our state space tree, we're going to understand that every time we have, we can either split or we cannot split, right? So if we want to split though, right? If we want to split, that would lead us to multiple branches down the line. So we can say it's going to be 2 to the power n, where n is the number of letters in a string. In other words, n is the length of our input string. And this is, again, exponential, but better than n power n, right? Even though it's going to grow exponentially with the input strings length increasing, it's not going to be as bad as n to the power n. All right, so this was about it. This was about pruning. So the only difference between this and this and our original backtracking problem is that we are making sure that we only go down a particular path if a particular predicate condition equates to true. If it equates to false, we are going to disregard that branch altogether. Now this was about backtracking and partitioning. We're going to be looking at one other combinations problem in our next video. Until then, happy coding.